Hello. Astronomy is the oldest science from all sciences. I think it's even older than maths. But a lot of people question how important is astronomy for us, for humans. Astronomy today is no longer astronomy. It's something, it's a soup of astrophysics, astrochemistry, astrobiology. So there's a bunch of sciences which affected astronomy and has created this platform, which we call today astronomy, but which is actually a very large science influenced by biology, chemistry, etc. But how important is astronomy? That's a question that I receive from thousands of people. Everyone wants to know, so why humanity needs to spend billions and billions to study the universe? Well, to answer this question, I want to start my lecture actually by posting a question to you, to readers. It's a very simple question, but you can try to think about this and come up with your answers. And if you have a brilliant answer, please send us an email. So the question is, now can you imagine humanity, human race, in the first stages of their evolution, about 100,000 years ago, 500,000 years ago, and we have no night sky. It's gray. There is a thick layer of clouds. We cannot see stars. We cannot see the moon. We can't even see the sun. So it's pretty much like what you have in the Nordic countries. Imagine Norway or Denmark, you live there, and you have no idea about the night sky. You don't see anything. How is going to influence this situation the evolution of human race? Are we going to be the same? Are we going to reach the same level of technologies, life quality as we have today? Or is it going to be completely different? Well, I have an answer. This is my answer. My answer, after a lot of brainstorming, is that we would have a completely different life, and the science would have been stopped, and this would haven't been a humanity. It would be a completely different thing. Even if there is no direct connection with stars, even if we cannot influence what is happening on the moon, but simply the fact that we have been observing a night sky for thousands of years has forced humanity to create, for instance, religions. The root of all religions goes to the night sky. And not just religions, so many things which virtually led us to build the space technologies, etc., etc. Anyway, my message is, if you think carefully, if you think very deep, you will understand that the evolution of a human race, of this society, would have been completely different without a night sky. That's very clear to me. All right, so astronomy was not evolving with large steps until maybe 19th or 18th century. Or basically, I would say until Galileo built the first telescope. The first telescope has changed. That was the first evolution in astronomy. So because then he realized that there are planets, they have size, and the motion of planets was discovered much before. But that was the beginning of observing a big universe. And only in the 20th century, we have been able to open this window of optical wavelengths, optical astronomy, that was used by telescopes, to much wider range of electromagnetic spectrum. So the 20th century is a century when astronomers started to use all sorts of instruments to detect radio waves, X-rays, gamma rays. We had to leave the planet and go to outside the Earth atmosphere to observe high energy electromagnetic waves. And from ground base, we could develop detectors to see infrared emission of celestial bodies. So astronomy in the 20th century became a multi-wavelength electromagnetic multi-wavelength astronomy. And that led to really big revolutions in astrophysics. This is when I can state that the revolution in astrophysics started in the 20th century. And obviously that was connected with revolutions in physics. And so the branch astrophysics was born in the 20th century and followed by astrochemistry, etc. And the first astrochemistry, actually, example is this picture of Andromeda Galaxy when we start using when we realized that a photographing technique can be used in astronomy. So the first photographs of galaxies have been taken more than 130 years ago. This is Andromeda Galaxy, which is made of 1 trillion stars at a distance of 2.5 million light years, with a size of 220,000 light years. And the picture shows the completely different system of stars, very, very far from Milky Way galaxy. That was the first high-quality picture of another galaxy. It's called Andromeda Galaxy. And 130 years later, we were able, with new technologies, first of all, with Hubble Space Telescope, to reach and study and zoom different parts of the Andromeda Galaxy. Here is a very nice video where you can see how we leave the Milky Way galaxy and we approach Andromeda. We go to one of the parts of Andromeda Galaxy, between spiral arms of the galaxy. We zoom and we see individual stars, millions of stars, which belong to another galaxy. So you can compare the size of Andromeda Galaxy, which is 220,000 light years, with the size of a visible universe, which is 93 billion light years. So here we zoom to the galaxy. The bright stars that you see here, most of them belong to the Milky Way, so they are projected. But the ones that are very, very small, very tiny, they're not big, those stars, like a haze, they belong to Andromeda Galaxy. So we have now a chance to study individual stars with spectroscopy and lights in a galaxy which is very far from us. But how expensive is to study the universe? It is very expensive. Well, it's not expensive if we compare this with what we spend in military on this planet, wars and all sorts of things. You can see probably the cost of one military aircraft is basically the cost of a giant telescope, whose goal is to push the limits of the knowledge of humanity and not destroy or kill. But that's what the humanity is. So we evolve in two different directions. Socially, we live, I think, in a few thousand years ago. We haven't developed that much, but technology has gone very far. And now we spend like $10 billion were spent to build the James Webb Space Telescope, which is probably the most advanced space telescope today. And we spend the same amount of money during 40 years on a Hubble Space Telescope. That's the maintenance cost, because just to build the Hubble was a couple of $1 billion. Then we have to maintain the telescope during 30 years, and that's very expensive. So the cost of most of the telescopes and ground-based telescopes and so on are billions, several billions. I can compare this with standard 1 or 2 meter telescope which were built in 60s. They would cost $1 to $3 million. So you can see the cost has multiplied 1,000 times. And a new generation of telescope which is coming to detect gravitational waves, a new generation of solar telescopes, that's all related to new technologies. And those technologies are very expensive too. For instance, I can tell you that to build a top quality high resolution spectrograph today will cost more than a 2 meter telescope. So you can spend 15 million, 20 million euros on a spectrograph, but only 5 million to build a 2 meter class telescope. So the technology today is more expensive than just polishing and making mirrors. And the duration and the timeline of different astronomy projects varies. Obviously, the space projects are the short time projects, typically between 3 and 10 years. Hubble Space Telescope was the only exception, which was extended to 40 years already. And because there were 2 missions with space shuttles to support, to upgrade the telescope. The rest of the projects are, space projects are very short. The ground-based installations, the ground-based telescopes, they can survive 40 years or 50 years. In fact, the ones that we are going to build now, the extremely large telescope, the 40-meter European telescope in Chile, is going to last at least 50 years, and it's probably going to be the largest telescope in the world for the next 40, 50 years. So you can imagine that we are spending 2 billion, but we are building a machine, actually kind of a time machine, that will last 40 years and will give massive discoveries, amazing kind of knowledge to humanity. So considering this, what we pay and what we get, I think is extremely cheap, because dividing this 2 billion for 40 years and considering the knowledge that we get from all these telescopes, I would say the telescopes are actually free. They don't cost money. The technology is also kind of a free thing. So we have to do more. We have to invest more, and that will be extremely rewarding. This is James Webb Space Telescope, the largest space telescope today, which is already operational for 6 months. We are receiving results from James Webb. This is the picture of the European extremely large telescope with a mirror 39 meter. It's a multi-mirror telescope, which will be commissioned in 3 years, will become the largest in the world. Here's the EELT, and there's a project for a 30-meter telescope in Hawaii, or probably it may move to Canary Islands because it's still not certain where it will be installed. And China was building fast 500-meter radio telescope now, and we have an array of millimeter, large millimeter, sub-millimeter telescopes in Atacama, in Chile, Alma. Those installations, those telescopes are ideal devices to detect infrared radiation, not infrared radiation, but long wavelength radiation from cool matter, from interstellar clouds, from planets in their initial phases of formation, protoplanetary or protostellar objects. And here is the square kilometer array, which is made of 3,000 dishes, each of them 15-meter size. So this is in progress and will be installed in South Africa and in Australia. This telescope is going to produce 157 terabyte data every second. So during 1 year, it will get 4.9 zettabyte data. And in 1 second, it will produce more data, 5 times more data than we have in entire internet. So you can understand that to store this data, to organize this data, to analyze this data, you need a special institution, special centers, and it would be impossible without advanced information technologies. And here is the evolution of telescopes, the sizes of telescope. In the last 40, 50 years, we were with 2, 3-meter class telescopes, 4, and now we moved, 50 years later, we moved to 40-meter class telescopes. So it doesn't simply mean having more mirrors, multi-mirrors, because this is not one dish. It's made of many, many small dishes. It's not just a matter of polishing quality and so on, but we have to manage to keep all these mirrors together, very well synchronized, to have a perfect focal plane, which is done with a special technology which we call active optics. So the active optics, without supercomputers, without developed softwares, will never work. So this is LSST, one of the top projects in astronomy today. the project aims to study 37, to discover 37 billion new objects in the sky during 10 years. So these 37 billion objects will be, I don't know, it will be galaxies, asteroids, comets, new planets, everything, free-floating planets in interstellar space. And every night we will get 15 terabyte data coming from LSST project. It's an 8.4 meter telescope designed and built in Chile. Will be commissioned, I think, very, very, very soon. And I would like to highlight that this telescope is actually going to discover lots of small bodies, asteroids around the Earth and between Jupiter and Mars. So these are potentially dangerous targets that can hit the planet any time soon. So discovering small objects, small asteroids, a couple of meters size, is absolutely important for astronomers. And here is the data collected by different telescopes. It's just simply kind of tables that show that the quality, that the amount of data that we are gathering from different telescopes is enormous, is huge, And it's just impossible with standard, simple softwares to analyze and to archive and to manage these data set. And an example of another astro data set, which shows how fast we increase amount of data in different astronomy projects and in different catalogs, the catalogs like Gaia and TUMAS and SDSS. So we are talking about terabytes and hundreds of terabytes of data. Mostly these are images and time series, and sometimes these are spectra stored in enormous databases. In fact, I have to highlight that astronomy is the only science where all this data is open for general public. So anyone can access these databases. If they have a knowledge, they want to study something, the database is open for general public. So no other science, not in molecular biology, not in the other branches of physics, nuclear physics or solid-state physics, nowhere you have open access data as much as we have it in astronomy. Data collected by all the satellites during the last 40 years, X-ray satellites like Einstein or XMM or ground-based observatories, even like Keck in Hawaii or in Canary Islands, all this data is stored in archives. It's free. It's free for anyone to use and to publish research papers if they can. They simply need to have a knowledge of doing this. And dealing with this amount of data, we have to perfectly handle the trinity of AI and machine learning, which based on computer, to compute, to develop algorithms, and to use the data which is stored in these archives. But the problem here is that we spend about 80% of time in organizing data, in gathering, in collecting the data, and organizing it. So it's too much. You can imagine you cannot spend 80% of your time just to collect the data and organize the data. So there's very little time left to analyze and understand the data. So that's why we astronomers start to use new algorithms and new softwares based on AI, machine learning, and deep machine learning to handle those things. These are a couple of breakthroughs in astrophysics of 20th century. I will mention you those things because they are all related to new technologies, and the future knowledge will come if we can handle perfectly and develop new tools, software tools, to understand this data. So first is expanding, accelerating universe. That was a discovery made in 2011 with a Nobel Prize for it. The cosmic microwave background radiation, which was a proof of the Big Bang. Extrasolar planets in 1995. Today we know about 4,000 planetary systems and more than 5,000 extrasolar planets have been discovered after 95. And we also realized where the stellar energy source come from in 1939, which is thermonuclear reactions. And in last century, we discovered a bunch of different interesting objects like quasars, pulsars, exotic objects, neutron stars, etc., black holes. And the challenge for the next 50 years is to open a new field, which is already open, the gravitational wave. Astrophysics is a field where you study gravitational waves and the sources that produce gravitational waves. These are supermassive black holes, collision of compact objects, black hole with a neutron star, etc., etc. And it gives you insights into the evolution of the universe during the next 100 billion years or so. Because that's another topic which, unfortunately, I cannot discuss it now, but it's one of the most interesting topics. What is going to happen with our universe during the next 100, 1,000, or 1 trillion billion years, when the whole fuel of the universe, which is hydrogen gas, is consumed by stars, and there is no more fuel left. So star formation will stop. Everything will end up in rocky, compact objects such as rocky planets, black holes, neutron stars, and so on. So what is going to be the future of the universe after there are no stars shining, there are no galaxies shining? So that's one of the very interesting questions in astrophysics today. And obviously dark matter, dark energy, gravitational singularity. And now I want to highlight a couple of examples where you can see how important was technology and is technology for astronomers. So very few people know that the proof that there are black holes in our galaxy came from a development of X-ray detectors. So the black holes have been discovered because we were able to develop X-ray detectors and take them out of the take them to the orbit on satellites. So in 1962, the first X-ray detector was on board of Arabi rocket, and the first X-ray source, Scorpion X1, was discovered. And 2 years later, which later turned to be a neutron star a binary system. And 2 years later, Cygnus X1, massive black hole, was discovered in '65. Many years later, it turned out that this is a system with a massive normal star, which is about 40 solar masses, massive bright star, and a 20 solar mass black hole in the system, in a binary system. That was the first galactic black hole discovered in 1965. And following, there was a Nobel Prize for this discovery. And so then we had lots of X-ray space telescopes to study the black hole systems. This is an example, is an accretion disk. The matter from the secondary donor optical star is accreted to the black hole, and this accretion process in the disk creates X-rays that we can see from the Earth with X-ray detectors. So the black hole is not seen, but we see X-rays produced in a disk of matter which is accreted by a black hole. So there is a list of about 20 galactic black holes that we know, this list will increase, but it becomes extremely difficult to detect them because the secondary stars are very, very faint. So we need large telescopes to discover those systems where we have binary black holes and a normal star. So the next challenge was the detection of gravitational waves predicted by Einstein. And the first indirect proof that the gravitational waves exist were done in 1974, where astronomers observed a binary neutron star system, is a binary pulsar, and they discovered that the period of the pulsar is decreasing in time. And it turned out that this decrease is happening because of the gravitational waves. So the system is losing energy, and that energy goes into gravitational waves. Again, that led to the discovery, led to the Nobel Prize by Hulse and Taylor. And following this, laser interferometer gravitational wave observatory, which we call LIGO, was developed for many years, and it became the most precise measurement machine that man has ever been able to build. So this machine, which is LIGO, can measure a change in a distance anyway, with a precision which is 10,000 times better than size of a proton. So that's only possible in astronomy. So you could develop this technology, which is very sophisticated, very complex technology, to measure a distance with a precision better than 10,000 times better than the size of a proton. So here is the experiment, and the gravitational waves that have been detected a few years ago came from a collision of two massive black holes of 35 solar masses. So another example of technologies applied in astrophysics and computational power is in supernova explosions. The supernova explosions are probably the most complex processes that happen in the universe. These are explosions of massive stars with masses more than 10 times the sun, that happen at the end of the evolution, when the whole energy in the star is consumed. There's no more hydrogen left and no more helium left. The star goes into runaway collapse, and which is producing afterwards explosion with very interesting physics, which converts implosion to explosion. So those simulations have been going on for many years, but only recently we were able to do 3D full hydrodynamics, completely with all the physics that we know today been put in these programs, in these softwares, and 50 million CPU hours are used to calculate just one model. So which means a couple of months with supercomputers and using actually parallel programming codes based on C and some Fortran 95. And those programs use enormous amount of computational power to calculate anything like this. So I'm not going to explain what is this in this picture, because it's part of the trajectories of accreting matter and the internal structure of the supernova. It's very complicated. In fact, to produce this picture, you need supercomputers. Again, only producing these animations and pictures, you can't do it with normal computers because it's so complex and so time demanding. So even picture like this needs a supercomputer, or these animations of supernova explosion, which is not homogeneous. You study these pictures in density profiles, the temperature profiles, and entropy to understand the physics of explosion. So this is an example of an animation. So the explosion itself is a very short process. It takes just a couple of seconds, the collapse and explosion. So supernova explosions are one of the fastest processes that happen in the universe, together with gamma ray bursts. And now the next I want to show you how we use artificial intelligence and deep learning to identify objects in the sky. This is an example of ultra deep field observed with Hubble Space Telescope. It's about 20 days integration of some portion of the sky to get deep and deep in images. Virtually, you end up seeing 10,000 galaxies. Basically, all the points you see on this picture are galaxies, not stars. And now, when it comes to identifying which is a star and which is a galaxy, because galaxies have different shapes, and we know their morphology, here are different types of galaxies, and there are also lots of nebulae, which also have different shapes. So your task is actually go through this picture and try to see what is a star, which is a nebula, and which is a galaxy. So doing this by eye in front of a computer is hopeless, because we are talking about millions of images like this. And if you have to cover an entire sky with a new generation of telescopes, and even with Hubble, it's just impossible to do this by eye, and even with standard algorithms. So you have to teach your computer, you have to teach, you need a teaching algorithm how to identify and learn in the meantime with your examples based on your database how to distinguish and how to separate different types of astronomical objects in the sky. And so for this, a new software called Morpheus was developed based on AI to identify targets. We use the same technique, AI and machine learning methods, to classify stellar spectra, because these databases contain tens of thousands, millions of spectra. Now, finally going to extrasolar planets, I want to mention that for today, we are only studying a small volume, only 300 light years away from the sun. And here we discovered these thousands of extrasolar planets. And the technique was based on spectroscopy, which you know from a school, it's based on a dispersion of light in a prism. And this is the spectra of stars, for instance, the solar spectrum, we call it solar DNA, containing 20,000 spectral lines belong to different chemical elements. We use this data to study the stellar structure, chemical composition, dynamics of the stellar atmosphere, and so on, and so on. And even here, we have about 15% of spectral lines still unidentified. So once we study the radial velocities of spectral lines due to the motion of a star, we call the curve radial velocity curve. This is a radial velocity curve of the 51 Pegasus, the first exoplanet discovered in '95, which was a giant Jupiter-sized object moving with a period 4 days around the parent star, 51 Pegasus. Here is the system. And today we discovered more systems like TRAPPIST with many planets. We are actually discovering copies of our solar system outside many hundred light years away. And there's a different technique which is using the transit of light curves. When the planet is crossing the stellar limb, we see the change in the darkness of the star. And using the depth and the duration, we can calculate the parameters of the planetary system. And if we use a transmission spectroscopy, so get the spectra of the star when the planet is crossing the stellar limb, we can have an idea about the chemical composition of the planetary atmosphere, detect the water. We use lots of space telescopes to study these processes. And these are the top high-quality spectrographs used to discover extrasolar planets. One of them, the first one was LOD with a precision 5 meters per second. Then the second generation came with HARPS. We dropped the precision to 1 meter per second. So this is the top spectrograph now called Espresso, which is in Chile, in VLT. Here we can reach a precision 30 centimeters per second to measure the radial velocity of a star. So this is super high. And then next generation is now, which is under development, is a laser comb calibration, which will take us to the precision 1 centimeter per second, which means we can measure stellar radial velocities and motion with a precision 1 centimeter per second and detect very small planets like Mercury, detect Earth-like planets around stars which are 200 light years away from us, with big telescopes. And the James Webb Space Telescope does observations of planetary systems outside solar system. And we can also use the same technique and the same technology, the spectrographs, to study surfaces of stars like the sun, the convection which is there, that's called stellar granulation. You can see these numerical simulations of granulation. Again, with supercomputers, we do 3D models of stellar atmospheres to study convection on the surface of a star. And those simulations help us to understand dynamics and the structure of stellar atmospheres with very high quality spectra such as these ones. And they also allow us to detect extremely faint spectral signatures in stars which belong to transuranian elements, to heavy nuclei such as thorium, uranium, and we can measure composition of those heavy elements, radioactive elements in stellar atmospheres. We know the presence of these elements is extremely important because later they will form Earth-like planets, and later those elements, nuclear, heavy transuranium nuclear radioactive elements, will be responsible for volcanic activity in these planets. So if we don't have enough amount of radioactive elements in planets like the Earth, there will be no volcanic activity and there will be no life. So that's one of the goals, to measure precisely abundances of those elements in stars like our sun. And finally, if we employ artificial intelligence and machine learning, we can study millions of spectra, high quality, very high resolution spectra of stars similar to our sun, and to detect any spectral signatures which are not common and which do not have a natural origin, which do not belong to any other chemical elements. So there have been speculations that these elements may belong to alien civilizations, to artificially created chemical elements, or enhancing the amount of certain chemical elements in the atmosphere of the sun, just to give a signal of the existence of extraterrestrial life. So this is where we can employ AI and machine learning, finally, even to detect life outside, intelligent life outside the solar system. So I want to finish my lecture with this very promising call that AI and machine learning may help in the future to discover alien life outside the solar system. And thank you very much.
Гарик, спасибо, очень интересно.
Да, спасибо за рассказ в такой области. Мы вообще заготовили много наших блестящих абсолютно вопросов, но в чате было еще больше, поэтому придется задавать не наши, а из чата. А нам так хотелось спросить. У нас были блестящие вопросы. Мы хотели узнать, круглая Земля, есть ли жизнь на Марсе, видели ли вы инопланетян в телескоп, кто вы по знаку гороскопа, в конце концов. Но придется задавать вопросы из чата. И первый вопрос такой. Используете ли вы технологии Яндекса, есть ли у вас доступ к технологиям Яндекса, или, подумав более реалистично, добавил наш читатель, технологии других больших компаний. Я, кстати, сразу хочу сказать, что можно смело говорить на конференции Яндекса, что нет, я технологии Яндекса не использую. У меня вообще соведущий из Microsoft, если что.
Нет, ну не только Яндекса, но и других технологий. Лично я только начал изучать AI и machine learning 2 года назад. Так что я пока еще новичок в этой области. Но я знаю, что мои коллеги, они обычно не пользуются коммерческими софтверами. То есть в астрономии наши начали работать с айтишниками или просто по контракту взять айтишников, чтобы они начали обрабатывать софтвер для астрономии, или чтобы они знали, что нужно откуда взять и так далее. У нас сейчас появляются люди, которых не было практически лет 10-20 назад, ребята, которые, они айтишники, но они очень мало знают астрофизику, они сейчас пытаются войти в астрофизику, да, но у них хороший knowledge по AI, по machine learning, но им очень трудно, потому что...
А нужно знать предметную область, разбираться в предметной области?
Знаете,
или достаточно хорошо знать ML, технологии?
Да, а кто же будет интерпретировать эти данные? То есть кто будет знать, доверяешь ты или не доверяешь? Я всю жизнь занимался программированием. Я начал мою диссертацию с программирования, написал код по радиационной гидродинамике, чтобы вычислить звездный ветер динамику звездного ветра у массивных звезд.
Не удивлюсь, если на Фортране.
Да, это Фортран, да, тогда это был Фортран, да. Потом я начал Фортран 90, параллельное программирование. Я даже читал лекции по Фортрану 90. Ну, потом все перешли к C++ или Python, сейчас все вот так.
То есть в чате довольно, на самом деле, много было, несколько вопросов, как айтишнику войти в эту индустрию, в эту область. Да. Правильно ли я понимаю, что все-таки какие-то специфические знания из астрономии надо получить?
Обязательно, да. И дело в том, что вот эти знания, они сейчас больше и больше. То есть то, что нужно знать сегодня в астрономии, это не то, что было 30 лет назад. Так что им будет очень трудно взять одновременно астрономию и быть айтишником. Я не знаю, вот как им это сейчас... У нас в институте есть ребята, которые пытаются вот и то, и так. Я сейчас изучаю просто, да. Но это нужно посмотреть, как эволюция будет, да. Сейчас просто экспериментальная такая фаза, да. Очень мало людей сейчас. Даже в астрофизике, вот ребята, которые занимаются классификацией звездных спектров, я их хорошо знаю, я сейчас на связи с ними, потому что у нас будет такая интересная коллаборация. У них студенты айтишники, они астрономы.
Кстати, вот если про обмен знаниями, у нас очень большое внимание, ну и раньше, и сейчас особенность уделяется open source. Ну и такому выкладыванию чего-то в общий доступ. Это может быть и код, и данные, какие-то площадки по обмену. Вот. А в
У нас все доступно.
Тоже
Астрономия
всё доступно.
это, наверное, я вот говорил, это единственная область, где абсолютно все каталоги, все данные за последние 40 лет доступны всем.
В связи с этим вопрос из чата, между прочим. Значит, слушатель спрашивает, зритель наш спрашивает, как вы относитесь, как вы оцениваете вклад астрономов-любителей на науку? Потому что, как раз, как я понимаю, данные открыты, и люди могут их самостоятельно обрабатывать. Вот. И человек говорит, что... передает большой привет, говорит, что он сам астроном-любитель, сделал год M45 фото. So technology is really amazing, говорит.
Да, да. Астрономы-любители уже лет 50, очень серьезно они работают. Я даже был на конференциях астрономов-любителей в Австралии. Я удивился, у них очень серьезные телескопы. Они отлично владеют вот этой техникой обработки данных и так далее, и так далее. Многие из них пытаются также теоретически знания овладеть, и многих у них есть даже публикации. Я видел статьи, где они публикуют с профессионалами вместе статьи. То есть они отправляют свои данные, наблюдения. Вначале это была только фотометрия. Стандартная фотометрия переменных звезд, интересных звезд и так далее. Да? Но сейчас уже спектроскопия. Потому что спектрографы сейчас не такие уж дорогие.
Вы не надменно относитесь, вы как бы приветствуете привлечение.
Да, очень-очень приветствую. Это очень здорово. Если они даже спектроскопию сейчас могут сделать, нормальный телескоп, потому что очень много работы по то, что follow-up, нужно следить за определенные очень интересные звезды в галактике. За ними все время нужно следить. Астрономы этого не делают. Потому что все телескопы на конкретные проекты, да, а вот следить, вот этим должны заниматься, наверное, вот наши любители.
Еще есть вопрос, какие инструменты в ближайшем будущем дадут прорыв в изучении экзопланет? Ну и вообще, как ML, машинное обучение помогает, или если помогает в обучении экзопланет?
Да, ну смотрите, вот сейчас после Кеплера будут еще другие по фотометрии, да, чтобы по методу транзитов найти экзопланеты. Будут много таких, но все-таки такая сильная deep learning, да, планет, это все-таки спектроскопия. Все-таки спектроскопия, а спектроскопия сейчас у нас эспрессо. Это самое классное. И скоро у нас будет работать эта калибровка с помощью лазерных лучей, это лазерком, то, что мы называем. И тогда это будет сильный прорыв. У нас будет точность 1 сантиметр в секунду. Мы можем, в принципе, копию Солнечной системы от Меркурия до Плутона изучать. То есть мы можем детектировать абсолютно все планеты в системе. Не одну или не две, а все 10, 12, 15 планет. Потому что точность у нас будет уже такая, да. А главное, что в астрономии нам нужна хорошая выборка. В закрытом пространстве, так сказать, volume limited, да, посмотреть в закрытом пространстве, сколько разных типов планетных систем. И чтобы понять, почему иногда образовываются такие планетарные системы, а в другой системе другие планетарные системы. Почему есть системы, где только 2 огромных Юпитера, маленьких планет нет? Потому что если были, мы бы нашли с точностью. Да? А есть системы, в которых практически больших планет нет, а есть такие маленькие планеты. В чем разница? Почему? Это может полностью хаотический процесс, или, может быть, все-таки какая-то физика есть, связанная с вращением Солнца, звезды, с начальными состояниями газа вот, и так далее. Да? Вот это самая главная задача. То есть мы не находим планеты, потому что это интересно. Нет. Мы обнаруживаем вот эти планеты, системы и все эти параметры вращения, периода и так далее, чтобы понять эволюцию и рождение. Как рождаются системы, почему они разные, и как будет эволюция вот этих систем.
Вообще, это, наверное, невероятно сложно, когда тебя приводят к людям, которые ничего не понимают в твоей области, говорят, вот давайте за 35 минут, ну, коротенько,
Да.
пара ответов, да, расскажите, что
Да,
про
да,
астрономию.
У меня немного наивный вопрос. Как относитесь к космическим инициативам Илона Маска? И вообще, что думаете про проникновение частного бизнеса вот в такие, значит, традиционно достаточно большие наукоемкие сферы?
Вы знаете, я сначала говорил, вот, мне очень жаль, что общество не понимает важность вот этого, то есть не инвестирует, а нужны частники, чтобы вот дать понять вот это, да, оказывается, так оно и работает. То есть в НАСА все спали, все сидели, никто ничего не делал, пока появился Илон Маск и сказал, ну, надо поменять, и надо лететь на Марс, и я сделаю вот это, и сделаю это. Это очень хорошо, это здорово. И слава Богу, что такие люди еще есть, могут рисковать своими деньгами до последнего, чтобы создать такую компанию, как SpaceX. С самого начала все говорили, что это ерунда, это ничего не удастся. Но поднять же компанию.
Так для этого приходите к нам, пожалуйста, чаще. Я не обещаю, что вас сейчас слушают
Да, на самом деле, судя по количеству
Илон
вопросов,
Маск, да, но разработчики точно
судя
слушают.
по количеству вопросов, да, вы заинтересовали своим докладом. Спасибо большое, Гарик. У нас вообще очень много еще вопросов, но, к сожалению, мы ограничены таймингом, так что
Вы же придете к нам еще раз?
Обязательно.
Здорово,
отпускаем вас. Спасибо.
большое.
Вам
Да,
спасибо.
отпускаем вас. Большое спасибо.
Спасибо.